Okay, so we're back here for Openstax Chapter 5, Thermochemistry. And here we're going to discuss Section 5.3, Enthalpy, and we'll break this up into two videos. This first one will be the longer of the two to discuss the theory behind enthalpy with a little bit of problems, and then the second video will have Hess's Law to wrap up Chapter 5. I recommend you have a piece of paper and a writing utensil in front of you to jot a couple key ideas from this section down. But before we get into those, we're going to proceed into a little bit of review, hopefully things that you retained from the first class that we had from Chapter 5, some of these broader themes of thermodynamics. Keeping in mind that thermochemistry is a branch of thermodynamics. In Chem 2, we will talk about thermodynamics as a whole, which deals with heat and work and other forms of energy and things like entropy and Gibbs' law. But thus far, we're only concerned with enthalpy. H, we discussed reactions being endothermic and exothermic, and we'll see those ideas again today. The key idea here is what Chapter 5 is all about, thinking about the energy behind chemical reactions and the fact that any substance, be it a molecule or anything else, acts as a reservoir of energy. Okay? And we talked about thermal energy before, and now we're thinking about energy as a whole, energy being added in, energy being taken out or removed. And that relates to the other intro idea we discussed, right? Kinetic energy of atoms or molecules. They're always moving unless we're at absolute zero. If we want to put energy into something, we're exciting those atoms or molecules and they're moving faster. So this is the first key idea I'd like you to jot down, the first law of thermodynamics down there at the bottom of the slide. First law of thermodynamics, delta U equals Q plus W. Q and W we've seen before, right? Q is heat, W is work, and now we have U, right, which is the internal energy of a substance, okay? The sum of all the possible kinds of energy that that thing can have, kinetic energy, potential energy, etc. Okay? Internal energy, U, and if you're looking at other sources, you may see this symbolized as E. Okay? And if we are lumping in those two categories, heat and work from before, okay, the sum of all the possible kinds of energy, delta U, is equal to Q plus W. And that delta, if it's a change in the internal energy, right, relates to how the amount of heat is changing, and if work is being done on the system or the system itself is doing work. That will change the value of those two variables, which is what this slide here, 54, is discussing. If energy is being put into a system, we're increasing the internal energy. That can be done one of two ways. Either it absorbs heat or something does work on the system to raise its internal energy. The example we used before was pumping air into a tire, right? That has a higher potential energy. We've done work to put air into the tire. Likewise, we can have a decrease in internal energy, either something releasing heat, right? If something is combusting, it's reaching a lower energy state, it's releasing heat, or the system doing work on the surroundings, right? If you do work, if you go to the gym, well, you can't right now because they're closed, but once they're open again, you go to the gym, you do work, you're more tired, you've reached a lower energy state. And these ideas are important because notice that the signs on those symbols change, which is a key idea, right? If you're absorbing heat, heat goes up, it's a positive Q. If you're releasing heat, negative Q. If work is being done on the system, it's a positive W. If the system is doing work on what's left, the surroundings, it's a negative W. And that's all summarized on this slide here, number 55 on my count. Remember, we talked about this big gray box when we were discussing calorimetry. We said that means we have a closed system. And so the sum of all these changes is zero because we have to abide by the law of conservation of energy. Okay? So we can either have work being done on the system or the system doing work, heating the system, or the system releasing heat to the surroundings. Okay? If the system is getting heat or work is being done on it, the internal energy is increasing. Opposite of those, the internal energy is decreasing. So if we think of one specific type of work, expansion work, right here, which relates to how an internal combustion engine works, right? What's going on in this situation? Okay, expansion work, pressure volume work. That's when we have a system pushing back up on the surroundings against some sort of a restraining pressure, like the pistons in an engine. Okay, so the surroundings are trying to compress the system, but the system is pushing back out. This is another idea that will come back in chapter 9 as well. Okay, so if we're thinking about our system, okay, gas and the oxygen that's necessary to combust gas, and the surroundings is everything else, okay, the entire universe, including the energy itself. Sorry, the engine itself, pardon me, getting ahead of myself. Now we should be obvious that the reaction, the combustion of gasoline is exothermic, right? Heat is being given off, okay? If you burn gas, it's hot. If the reaction is also doing work in driving pistons outward to power a car, it's also doing work on the surroundings, right? The engine in that case. So both Q and W are negative. So obviously the internal energy, because U is equal to Q plus W, right? If these are both negative, delta U has to be negative as well. Tells us that the internal energy of the system decreases. Okay. And internal energy is a unique situation that's known as a state function. Okay. Also known as a state variable, but in this course I'll use the phrase state function. And most things that we'll deal with in chemistry are state functions. What is the definition of a state function? Which is an important idea because we're getting towards enthalpy in this chapter, and enthalpy is a state function. The value of a state function depends only on the initial and the final states. Doesn't matter how you get there. So the example that is used in the text on here in the next slide, right, your altitude or your elevation, those are state functions. Okay. Going from sea level, right, 0 meters, to the top of Mount Kilimanjaro, okay, just shy of 6,000 meters, you've obviously increased your altitude. And at the end of the day, if you're at the summit at 5895 meters, it doesn't matter if you hiked to the top, you parachuted out of an airplane to get to the top, you rode on the back of a Sherpa to get to the top, you hop, skip, jump, rollerbladed to the top. It doesn't matter how you got there. At the end of the day, right, your final elevation is a state function. Okay, doesn't matter if we're staying hiking, you went straight to the top, you took a twisty, topsy-turvy route to get there, you're still at the same final elevation. That's what a state function is. Okay, the example that I use in class, I have students jump on the top of a table. Okay, one person jumps, one person sits on their butt and then hoists themselves up. Another person uses a chair to get up there. But at the end of the experiment, if you will, right, everybody's at the same height. Okay, that's a state function. Adding money to a bank account is a state function. If you go to a bank teller and you give them 100 singles or 5 20s, at the end of the day, right, you've increased your account balance by $100. Doesn't matter how you got there. Another example of a state function. So where is that useful in chemistry? Right, we're getting to this idea of enthalpy. Okay? Enthalpy is a state function. And enthalpy, which is a huge idea from this chapter, right, H, is defined as the sum of the system's internal energy, which we saw before, U, and the product of its pressure, right here represented by P, and its volume represented by V. As I just mentioned, enthalpy is a state function. Right? And we can't measure the enthalpy value that something's at, directly measure a specific substance's enthalpy. We look at enthalpy changes, right? Again, delta representing change, and that's a big area of interest in chemistry, the enthalpy change for a reaction. Okay, we see the same delta here that we saw before for delta U, right? Because these things relate. If we're looking at the enthalpy change, delta H, it's the change in the internal energy plus the atmospheric pressure multiplied by the change in volume. Okay. But the nice thing is, right, if we are doing a reaction on the benchtop, for example, right, this reaction is going to occur at a constant pressure, right? The atmospheric pressure in the lab is not going to change appreciably. Okay? So we can think about the fact that this is going to be relatively constant. Okay? And P delta V, pressure times change in volume, is the same expansion work that we were discussing before. Okay? And if we think about P delta V as being equal to negative work, right? Those are going to always have the opposite sign, because if pressure is constant, delta V, if the volume is increasing, the only way for that to happen is for work to have been done on it to expand the volume, right? So those have to have opposite signs, right? The system has to have done work to expand the volume, therefore it lost work, negative W. So if we put all of those ideas together, right, delta U equals QP plus W, okay, and then we substitute out what we just said with the pressure volume change, right? At a constant pressure, the enthalpy change is equal to the heat of the reaction. And notice on the slide here, I want you to know the relationship for a test or a quiz. I won't specifically quiz you on the derivation, right? But be familiar with the fact that QP, right, subscript P here tells us we're at constant pressure. So QP is the heat of the reaction at a constant pressure, and now that is equal to enthalpy. Okay? So if you want to jot that down, enthalpy is equal to the heat of the reaction at a constant pressure. Okay. We already discussed the fact, right? Everything pretty much that's already on this slide. Open containers, normal atmospheric conditions, constant external pressure, right? Heat flow and enthalpy process are equal. Yep. So we're considering enthalpy to be the most convenient choice for determining the heat of a reaction. We've said all of that in the preceding slides. Okay. So now we jump into thermochemical equations. And now if I can represent the enthalpy change for a reaction, I can introduce that idea and relate it to a thermochemical equation. A thermochemical equation represents changes in matter and energy, okay? Because previously we were just doing balanced reactions. Okay, make sure the atoms on the left is equal to the atoms on the right. That's a balanced chemical equation. A thermochemical equation also has the enthalpy change reported with it. Okay, so notice here we've got a balanced chemical equation and then the corresponding enthalpy change. Delta H equals negative 286 kilojoules. It's an exothermic reaction. Okay? And what that delta H value is, this is what the note on the bottom is referring to, is the amount of heat associated with the reaction exactly as it's written, which is why we can get away with using this coefficient of 1/2 right there. Right? In the preceding 4 chapters this semester, we said that those coefficients always have to be whole number ratios, right? But in a thermochemical equation, you can use a non-integer coefficient like that, because that enthalpy value, delta H is equal to negative 286 kilojoules, is the enthalpy change when I have exactly 1 mole of hydrogen reacting with 1/2 mole of oxygen. If I change those numbers, I change the enthalpy value that's written to the right. And these are really important ideas for using Hess's law in the next video. Okay? So think about this like balancing a reaction, right? If I'm balancing a redox reaction to get my electron count to equal the same on each side, right? I have to multiply everything in a reaction. Okay? So this is what I was referring to before, right? Enthalpy is an extensive property. So if I double my amounts to get, instead of a 1 to a 0.5 to 1 ratio, now 2 to 1 to 2, if I double all those coefficients, my enthalpy value then doubles from negative 286 to negative 572. Okay. Here I'm multiplying by a factor of 2. I could have chosen to multiply by anything else. 3, 4, 5, 1/2. Okay. Anything like that. You just have to treat the entire reaction and the enthalpy value the same. Okay. Another thing with thermochemical equations, and I've been trying to get you in this habit for the beginning part of the semester, right? The enthalpy value does depend on the states. Notice 2 reactions here. Both of them are H2 plus half O2 goes to H2O. But the top reaction is two gases forming a liquid. Bottom reaction is two gases forming a gas. Here, the delta H value changes. Okay. So when you're writing a thermochemical equation, the good news is you can get away with writing those non-integer coefficients. Right? The bad news is if you do not show your physical states for everything, all the reactants and products, you won't get full credit on that. So jot that down. You always have to show the physical states of everything, because as those physical states change, the enthalpy value changes as well. Okay. The direction that a reaction goes is important as well, because we discussed this in the first lecture from chapter 5, right? If a reaction is exothermic in one way, it's endothermic the other way. Okay. So I have to specify which way my reaction's going, and I can flip the reaction around, and that just flips the sign for my enthalpy value, right? So sticking with this same reaction up top, right, our delta H value is negative 286 kilojoules. If I flip that reaction around, and I have to flip it 100%, right, all my reactants become products, all my products become reactants, and then the sign of my enthalpy value flips from negative 286 to positive 286 kilojoules. So an example to show this, okay, a gummy bear contains 2.67 grams of sucrose, and we're asked with that reaction to calculate the enthalpy change for the reaction. Now this is a kind of an involved reaction, or involved problem, pardon me, because it does involve first calculating the limiting reactant, 2.67 grams of sucrose and 7.19 grams of potassium chlorate. This experiment is called Death of a Gummy Bear. If you want to search that on YouTube, pretty violent exothermic reaction, looks cool. Okay, so we have 2.67 grams of sucrose, 7.19 grams of potassium chlorate. We have to first calculate the limiting reactant. Okay, take both of those values, convert them to moles, pick one of the products, figure out how much I could make, whichever one makes less as the limiting reactant. Then I use that information to calculate the enthalpy change for the reaction. So pause the video now, give that a shot. Okay. Calculate the limiting reactant. Is it sucrose? Is it potassium chlorate? Okay. And then 43.7 kilojoules is the enthalpy change for the reaction as it's written, right? With those amounts coming together. We're concerned with calculating the enthalpy change for the reaction when I have exactly 1 mole of sucrose and exactly 8 moles of potassium chlorate. Okay. I will upload a separate video onto YouTube here showing how this problem is solved step by step. But before you watch that, give it a shot, and the answer is shown on the slides as well. I should get a final answer here of negative 5,960 kilojoules. I'll have a separate video showing how that's found step by step. I think this video has gone on long enough already, so I'm going to stop here and then start the second video, well, the third total video for this chapter a little bit earlier, where we'll talk about standard state and Hess's law.